In our third video on stepwise multiple regression, we'll continue with our example, now looking at Model 2, the second iterative step in our stepwise model building, after Model 1 in which we started with just mother's education. So here's our Anova table again. Remember, this summarizes the effect for the overall model at each step, the effect of all the predictors in that step, together as a set or a team. Focusing on Model 2, the superscript C at the very end tells us that our predictors are both mother's education and school quality. Now, notice the model has automatically added school quality as a predictor, just like we expected, based on the excluded variables table at the end of Model 1. And the overall model with both predictors is statistically significant, with an F with 2 and 397 degrees of freedom equal to 32.685 and a p-value less than 0.001. Notice how, as we've added one variable, the degrees of freedom regression increases by 1, and the degrees of freedom residual has gone down by 1. Now, remember that 397 for the residual degrees of freedom, as we're going to need that later. So the overall model is statistically significant, but remember at this point we're still model building. The question isn't whether the model is significant, it's whether what we've added is significant. If you have a statistically strong model and add garbage, the overall model may still be significant even if you've added some useless variables. So we're really not interested in the Anova table at each step of the model building phase. When we're doing stepwise analysis, we're really only interested in it at the end with our final model. Similarly, in the model summary table, we see that the total R-squared for Model 2, including both mother's education and school quality, is 0.141, or the set of both variables accounts for 14.1% of the variance in grades. But again, in the model building phase, we're really not interested in the total R-squared at each step. We'll be interested in the total R-squared at the end with the final model, but not at each step. While we're still building the model, the thing that's most important is how much the R-squared increased and the degree to which that increase is statistically significant. So let's look at the change statistics, right? This shows the increase in the change in R-squared when we've added school quality, which is just our current R-squared at 0.141 minus the Model 1 R-squared of 0.128, or an R-squared change of 0.014. Trust me, that's correct if we reported more decimal places for our R-squareds. Now, in terms of variance, this is the unique effect of school quality controlling for mother's education. Now, of course, this increase will be statistically significant, or stepwise multiple regression would not have added it to the model. But what is the test for whether that 0.014 increase in the R-squared is just random noise and maybe the effect of school quality controlling for mother's education really is zero out in the entire population? That's what our F change test does. We see that our F with 1 and 397 degrees of freedom is equal to 6.331, and our p-value for this change in R-squared is equal to 0.012, which means it is statistically significant. Now, remember these values because we'll come back to them in just a minute. Now, looking at the coefficients table, let's focus on Model 2 and the coefficients for this model that includes, again, both mother's education and school quality. The new regression model is our predicted outcome, our predicted y, our predicted grades, is equal to 0.073 plus 0.119 times mother's education plus 0.043 times school quality. Let's focus specifically on school quality for a moment. Controlling for mother's education, school quality is statistically significant with a B, unstandardized regression coefficient of 0.043, and T with 397 degrees of freedom, remember our degrees of freedom from earlier, is equal to 2.516 with a p-value of 0.012. Don't add an extra zero there. Now, notice that this is essentially the same result that we saw with our change in R-squared test. Because remember, if you square a t-score, you get the f value that you would have obtained if you'd used an f-test instead. And squaring 2.516 gives us 6.331, the f-score from the change in R-squared test. Given that, it should be no surprise that it's also the same p-value. And if you think about it, this makes sense. The regression coefficient is the unique effect of school quality controlling for mother's education in terms of school quality scores. And the change in R-squared is the unique effect of school quality controlling for mother's education in terms of variance. You can also see one other equivalence here, and that's that in the step in which a variable is added, the squared semi-partial equals the change in R-squared. See, we added school quality, and if we square that semi-partial of 0.117, we get 0.014, which is the change in R-squared in Model 2. They're both the same thing. They're both the unique effect of school quality controlling for mother's education expressed as a variance. Pretty cool, isn't it? Now, this only works because we've added a single variable. Later, we'll see that if we added several variables together as a set, the change in R-squared when that set is added obviously won't be the same as the squared semi-partial for individual variables in the set. But in stepwise multiple regression, variables are only added one at a time. So in that case, the change in R-squared and the squared semi-partial are the same thing in that step in which the variable is added. I mean, of course, they won't be equal in subsequent steps because the semi-partial will change as we control for more and more variables. Okay? Just a little interesting thing in case you noticed that. Now, while we're here, let's also look at mother's education. Okay? Controlling for school quality, mother's education continues to be statistically significant with a regression coefficient of 0.119, and T with the 397 degrees of freedom again is equal to 6.684 with a p less than 0.001. Now notice that compared to Model 1, it's the same variable, mother's education, but the effect is different. That's because now it's the unique effect of mother's education controlling for school quality. It's the effect of mother's education that's unrelated to school quality. Consequently, the regression coefficient and the statistical test will change. Finally, notice that both variables meet our criteria for staying in the model. Our p-out rule was that we would kick out a variable if the p-value was greater than 0.1. And all, well, in this case, both of our predictors have p-values less than 0.1, so they would both stay in the model at this point. Now, looking at the excluded variables table, we see that for model 2, we have 2 remaining variables that are not yet in the model, father's education and study hours. But neither of these meet our entry criteria of a p less than 0.05, so neither would be entered in a potential third iteration, a model 3. Plus, as we just saw in our coefficient table, based on our criteria, we don't want to drop any of the variables currently in the model. So the stepwise model building will stop at this point. This is our final model. So that's the process for a stepwise multiple regression analysis. Variables are added and removed from our model one by one until everything in our model meets our criteria for being in the model, and none of the variables that are not in our model meet the criteria for entering our model. Okay? Now, there are other variations on this in and out approach. One is what's called forward selection or forward entry. It's similar to stepwise in that we start with an empty model and add the variable with the largest effect, and then keep adding new variables that have the largest remaining effect and that meet our entry criteria. The difference is that with forward selection, once a variable enters the regression model, it cannot be removed no matter how small the effect may become later on. As a result, the final model may include some variables that no longer meet the entry criteria or are even statistically significant. Consequently, forward selection may produce a larger model than you may have obtained if you just did a straight stepwise multiple regression. So it's an approach one might consider, for example, if one is looking for a comprehensive list of possible variables for further investigation. Now, it's worth noting that some people may refer to forward selection as stepwise, but they're not the same thing. You can think of stepwise multiple regression as a class of procedures and also as a specific approach within that class, while forward selection is one type of this group of stepwise approaches. Now, alternatively, there's what's called backward removal. It's essentially the opposite of forward selection. You start with all the possible variables in the model and then successively remove the variable with the smallest unique effect that also doesn't meet your inclusion criteria. And once a variable has been removed, it cannot re-enter the model. Now, again, it can't re-enter the model even if later on it would be statistically significant once there's fewer variables in the model. Once it's out, it's gone. Consequently, backward removal may produce a smaller model than you would have obtained using a straight stepwise multiple regression. So it's an approach one might consider, again, in this case, for example, if you're looking for a more focused, concise list of possible variables for further investigation. Now, in summary, notice I started talking about this as the bad, and I do not use the term the bad loosely. It really is a problematic approach, and as such, it has fortunately fallen more and more out of favor over the years. This is incredibly data-driven. You're testing each variable over and over and over and over again. Each step involves conducting a t-test of every variable, both those in the model and every single variable on that potentially long list of variables that are not in your model. And then you test every one of them again on the next step, and the next step, and the next step, and the next. You really are fishing for effects. And while we would all like to spend the day fishing with Brad Pitt in Montana, it's not the best approach for science. Because you're doing so many tests, you're going to make more type 1 errors. In other words, your final model is at risk of including variables that really have no effect in the population. In fact, the idea of an alpha level is pretty meaningless in stepwise models because you're doing so many tests. And because stepwise models include more variables that are just type 1 errors, they also have problems with replication, right? A model full of random noise and type 1 errors won't replicate. Now, some say that you can use stepwise multiple regression if you're only predicting scores. But even then, there are other approaches that are better, and many methodologists, and I, would discourage using it. And you definitely can't use it to infer the relative importance of variables or explain effects, even though some do anyway. So, is it clear that I strongly discourage you from using stepwise methods? I've tried to make it sound bad, and in practice, it's often much worse. But you should be familiar with it so that you know the problems if you see someone using it. Plus, it's a nice tool for introducing ideas like multiple models and change in R squared. So, the lesson here is keep away from the bad. Stick with the good or simultaneous multiple regression, or you can go with the approach we'll cover in our next series, the ugly or sequential multiple regression. Okay? That's it for this video. Take care. Bye-bye.